Hi class, today I'm going to be covering naming of oxyanions, acids, and hydrated compounds. Oxyanions. Most polyatomic ions are oxyanions. They are anions that contain oxygen and another element that's a nonmetal. When a series of oxyanions contain different number of oxygen atoms, they are named according to the number of atoms, oxygen atoms in the ion, but they all keep the same charge, meaning if there's a family of them. For instance, if you look down here, we have sulfate and sulfite. They have the same charge, however, they have different number of oxygens. So that's what it means by a series. If there are two ions in the series, the one with more oxygen atoms ends in an 8, and the one with fewer ends in an ite. So you can see again, if we go back here, sulfate, the 8 ending has 4, and the ite ending has 3. So if you ever hear sulfate, you should know that that's the one with the most, and sulfite has the least between those, nitrate and nitrite. If there are more than 2 ions in the series, for instance, as you can see here with these, then the prefixes hypo, meaning less than, and per, meaning more than, are used. So for instance, you can see here we have ClO all the way down, but this one has 1 oxygen, this has 2, 3, and 4, but they all say with the same charge. So in order to account for this, we have to keep the naming similar, but we've got to change some things so that you understand which one you're dealing with. So the one with the least amount of oxygens, in this case is 1, it would be hypochlorite. Ite also indicates less, smaller amount of oxygens. So hypochlorite. Then we have 2, so we remove the hypo and it's just chlorite. Then we have 3, so now we have the ending changed to 8, meaning more oxygens, and it's chlorate. And then we have 4, and this is the most oxygen in this series, so it's going to be perchlorate. And the same thing applies over here. You can see hypobromite, bromite, etc. And then here is just some rules, exactly what I just went over. The least oxygens has the hypo, the root name, and ite. The most has per, the root name, and 8. And you can see exactly what I went over on the previous page. So that's the oxyanions. Now we're going to cover acids, which are also going to bring the oxyanions back in. Acids are molecular compounds that release hydrogen ions or protons when dissolved in water. Acids are composed of hydrogen, usually written first in the formula, and one or more nonmetals written in the second. So HCl is a molecular compound. It's a gas, but when it's dissolved in water, it forms a proton and then Cl minus, which is an anion, even though they're both nonmetals. We treat them as if they're ions. If it has an AQ, in the physical state, then that means it stands for aqueous solution, meaning this was dissolved in water. This is very important because the physical states tell you what you're dealing with. In this case, if it has AQ, we're dealing with an acid. But if this here, HCl, has in parentheses G, it's a gas, and it would be named completely different outside of what the acid is. So here we're going to look at 2 different type of groups. We have binary acids and oxyacids, which are from our oxyanions. So binary acids both have, and oxyacids both have an H plus cation, but the binary deals with a nonmetal anion, usually a halogen, and oxyacids deal with polyatomic anions. So we're going to cover the binary acids, and binary means 2. So this is two elements with this. So first we write the word hydro as the prefix, follow with the nonmetal name, and change ending on nonmetal to ic. Write the word acid at the end. So, for instance, if we have hydrogen chloride as a gas is named hydrogen chloride. But once we have it dissolved in water, it is now an acid. We no longer are going to follow the naming for this. So if we look up here, we immediately add hydro, and we're going to take the base name of the non-metal. So we're focusing on the second portion of this. So it's going to be the chlor. So we're going to have chlor, we're going to add hydro, and then we're going to change the nonmetal name to ic and add acid. So this would be hydrochloric acid. So again, if we have hydrogen bromide as a gas, it's named differently. But the minute this dissolves in a water, it's now an acid. So we take the base name of the nonmetal. So we'll look at the second half, which is brome. We're going to add hydroic acid, and this is now hydrobromic acid. And this is usually for halogens and how they're named. Naming oxyacids. If you have a polyatomic ion ends in 8, then change the ending to "ic" suffix. If the polyatomic ion ends in "ite", then change the name to "ous" us suffix. Write the word acid at the end. So again, here's some examples. Here we have the oxyanions, but now they're in acid form. So oxyanions ending with 8, we changed the 8 ending to "ic". So we have now chloric acid instead of chlorate, and we have perchloric acid for the for the one that has 4 oxygens. Excuse me. Oxyanions ending with "ite", we would have now changed this to "ous". So the least amount of oxygens is hypochlorous acid, and the second, the one right above it, which has, or below it in this case, has 2 oxygens, is chlorous acid. And then here I put a chart here so you can see the same thing that we just went over. We went over the oxyanions, and now you have the corresponding acid name that matches and what is removed and what is added. Also, I put this chart. This chart was different colors, so that's why it looks weird, because I tried to keep it one color. You can see the acid form, the acid name for a few of these, the oxyanion name, and then the oxyanion formula as well. So an acid naming recap. When the name ends in acid, formulas start with H. Hydro prefix means it's a binary acid. No prefix means it's an oxyacid. And for oxyacids and oxyanions, you can make sure you understand the ending and which ending replaces it with. So if it's ending in "ic", the polyatomic ion ends in 8. And you see the example here. If it's ending in ous, polyatomic ion ends in "ite". Now we get into hydrates. Hydrates are ionic compounds containing a specific number of water molecules associated with each formula unit. The water molecules are incorporated into the ionic compound and are accounted for. So these are not just hanging around because they're attracted to it. They're actually incorporated into the lattice structure. And in order to remove them, some are very easy that they will just, with low heat, can leave, and others take a lot more than just that to remove them. But there's 2 things you need to know when you're dealing with hydrates. Determining the mass of the complete hydrated compound, you have to account for the waters and how many waters are attached. And you also have to account for the waters in the name. So as an example, I'm going to show you here. The formula for Epsom salt is magnesium sulfate. So magnesium sulfate itself should not be something that you haven't seen before. You should be very familiar with this, especially with this chapter. But we have to account for the waters. In order to do that, there's a dot. This dot doesn't have to be like this. This is the only one I could find on this program. But it's usually more in the middle, but any kind of dot. But it's got to be a dot, a black dot. And then the number of waters that are included with this formula unit. So this has 7 waters that are attached. So this is called waters of hydration. So in order for, if you were to do the mass, you would take the mass of this, plus you would have to account for, in this case, 7 water molecules, or the 14 hydrogens and 7 oxygens. They have to be added into the mass. Now the naming of this, you also have to indicate it's a hydrate. So this would be magnesium sulfate, which is just this here, hepta, the 7 hydrate. So you have to include the number and the actual word hydrate. And that's how you know you're dealing with the hydrated compound. So I've included here where you can see that the name of the ionic compound, a dot, the number of waters of hydration, which is just a fancy word for water molecules and how many there are. And then you add hydrate. Now the opposite of hydrated is anhydrous. Anhydrous means no water. This is dry, is what they call it. Why do I know this? Because I work in a lab still. I don't know if I've mentioned that. And I order items or chemicals that are anhydrous. They need to be anhydrous. We want absolutely no water with these compounds because when we do reactions, the water, if there's any kind of water that, especially moisture in the air, can pull into a compound that it really wants to take it in, if the cap's left off, will no longer be what it should be. And now impurities will happen. I'll get different products. So we buy anhydrous compounds and we keep them in a very sealed container away from anything that could take in water. So when you hear of anhydrous magnesium sulfate, that means it's just straight the ionic compound and no waters are attached. The number system is something that you should already be familiar with. I'm going to show you up to 10. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. So here's another example I put together. So if you had 6 waters attached to an ionic compound, say copper 2 sulfate, then you would write it out copper sulfate the correct way with reducing the 2's. The copper 2 has a 2, the sulfate has a 2, you reduce those out, put the dot, 6, and H2O. Now this means that this is a hydrated compound, and how you say it is copper 2, parentheses, and the numbers go with it, there's no space, sulfate hexahydrate. And this is how you would handle any of these. Not difficult, just remember if you have an ionic compound, you have to add a dot, the number of waters, and the water H2O itself. And then when you write it out, you would write this out as normal, but now you would write out the number of waters and hydrate. It's important to indicate that you're dealing with a hydrate and not just an ionic compound by itself. Okay, and that's it. I hope this makes this a little bit more understanding in this chapter.